All right, guys, so what we're doing today is 5, 2, 3, adding and subtracting like radicals and roots. For us to be able to add or subtract like radicals or roots, the terms have to be the same. So when we look at a, the fourth root of 10 plus 7 times the fourth root of 10, we want to be able to add or subtract. Now, one thing we have to do is make sure that our radicals are simplified as possible. And the fourth root of 10 is as simplified as it gets, because if we looked at the prime factorization of it, well, 10 is just 2 times 5. So we can't simplify there. So we need to see how we can add these two together. I'm going to write it out in a way that will make sense and explain how this works, but you don't have to write this. Because if we look at this here, both of these expressions, both of these terms have the fourth root of 10 in them. So they do have a greatest common factor of the fourth root of 10. And what I can do is I can factor it out of both. If I factor the fourth root of 10 out of the fourth root of 10, I'm left with 1. If I factor it out of 7 times the fourth root of 10, we're left with positive 7. Telling me that I have the fourth root of 10 times 1 plus 7, which is 8. And if we multiply those back together, telling me I have 8 times the fourth root of 10. Or they both have the fourth root of 10, so that means they're like terms. I have one of them, and I'm adding 7 to it. 1 plus 7 is 8, telling me I have 8 fourth roots of 10. Okay, you can just put that on my desk. Questions on the first one? If we look at the next one, I have 2 times 8 to the 1/5 plus 10 times 8 to the 1/5. I mean, we could write 8 as 2 to the 3rd, which would be 2 to the 3/5, but it doesn't simplify any further than that. But what this is telling me here is I have 2 of them, and I'm adding 10 more to them because they both have 8 to the 1/5. So 2 plus 10 is 12, 8 to the 1/5. There are 12 of them. Questions on A or B? C, third root of 54 and the cubed root. So cubed root of 54 minus cubed root of 2. Are those like radicals? No, so there's a good chance that we need to simplify it, especially the cubed root of 54. Because if, I'm going to write it a little bit lower down, if I had, say, something times the cubed root of 2, bless you, minus the cubed root of 2, if both of them had cubed root of 2 terms, or cubed root of 2 is part of their number, I could actually subtract them, yes? So that means there should be a perfect cube, a number times itself 3 times, contained in 54. A few ways we can do it. One, factor tree. And I know one of the factors has to be 2, because that's what we ended up with. Well, it would be 2 times 27. 27 is 3 times 9, and 9 is 3 times 3. Telling me this is 2 times 3 cubed. We can use our product property with roots. The cubed root of 2 times 3 cubed is the same as the cubed root of 2 times the cubed root of 3 cubed. Well, cubed root of 2 is not going to reduce, it's just cubed root of 2. But the cubed root of 3 to the 3rd is what? 3. So we're saying that the cubed root of 54 is equivalent as 3 cubed roots of 2. Now do both terms have a cubed root of 2? Yes. So I'm really looking at 3 minus 1, which is 2 cubed roots of 2. And again, we can check this. Cubed root of 54 minus cubed root of 2. Cubed root of 54 minus cubed root of 2 is this decimal here. And we're saying this is the equivalent of 3 times the cubed root of 2. Make sure I typed it in right. 2 cubed roots of 2. Help if I get my numbers right. 2 cubed roots of 2 is the same as the cubed root of 54 minus cubed root of 2. Lo and behold, we do see that they are equivalent expressions. Questions on these here? Let's look at 10, 11, 12. 10, 7 times the fifth root of 12 minus the fifth root of 12 would be 6 times fifth root of 12. Fifth root of 12 is as simplified as it gets. Because if we wrote it out as the product or its prime factorization, it'd be 3 times 2 squared. There's not 5 factors anywhere in it. 4 times 9 to the 2/3 plus 8 times 9 to the 2/3 would be what? 12 times 9 to the 2/3. 4 plus 8 is 12. 9 to the 2/3, I mean, we could rewrite it as 3 squared. R squared, our power of 2 times 2/3 would be 4/3, telling us that we have 3 to the 4/3. But 3 to the 4/3 does not reduce nicely, neither does 9 to the 2/3, so they are equivalent statements. Let's look at 12. For us to be able to add these, we really need to be able to rewrite the cubed root as 40 as something times the cubed root of 5, yes? Would we agree with that statement? Because if both of these had the cubed root of 5, we'd be able to add them. So that means whatever times 5 that gives us 40 should be a perfect cube. Well, 40 divided by 5 is what? 8. What is the cubed root of 8? 2. Which begs the question on the last one, because our number was 54, and we needed to have left a 2 left inside, yes? Well, the cubed root of 27 is 3. For us here, that means that 2 times cubed root of 5 should be equivalent to the cubed root of 40. Cube root of 5 plus 2 cubed roots of 5 would be 3 cubed roots of 5. So with a lot of these here, and what we will be doing, we will be able to use the other radicals as hints and let it hint us and give us a direction of where we're going. Because I knew the one had the cubed root of 5, the other has to have the cubed root of 5. We can use that to figure out what else is going to reduce that. Questions on this here? Properties of radicals, especially with variables. This is specifically with variables. If I take the nth root of x to the n, it is going to equal x if n is odd. Because if I take the odd root of a negative number, it's still going to be negative. If I put a negative number to an odd power, it will still be negative. It doesn't change what it is. However, if I put it to an even power, it's going to change what it is. Because I cannot take an even root of a negative number to an even power and get a positive or get a negative back. And they show it here because the fourth root of 3 to the fourth is 3. Because 3 to the fourth is positive 81, the fourth root of 81 would get us back to 3. However, if I take negative 3 to the fourth power, negative 3 to the fourth power would be positive 81. Fourth root of 81 is still 3. So we cannot say that the fourth root of negative 3 to the fourth is negative 3. It's going to have to be positive 3 because of how our powers work. So if we take the even root of an even power, we have to put the absolute values around it to signify that it cannot be negative. Questions on this here? The only time we don't have to put these absolute values is if the power left over to that variable is even. So if when we simplify down, we are left with x squared, we don't need the absolute values because squaring something is going to make it positive. However, for the most part on the homework and what we do, I will not be concerned with that. So what we're looking at here is the cubed root of 64y to the 6th. So we have two main parts. One, we're taking the cubed root of 64, and we're also taking the cubed root of y to the 6th. Cubed root of 64 is nice because it is 4. Now our cubed root of y to the 6th. Especially with variables, instead of trying to figure out grouping and doing different things with this here, we can look at it as a to the x over n. And for us here, it's going to be y. Exponent attached to y goes on top, so it'd be 6. The denominator would be the root, which is 3. 6 divided by 3 is 2. Telling us that we have 4y squared. Now, because we did not apply an even root to it, an odd root to it, we don't need the absolute values. So it's just 4y squared. The other way we could have done it is we could have left it as a radical. I'm just going to put this as a side note. What we could have done with this here is wrote it as the cubed root of y squared cubed. Powers of powers multiply, so 2 to the third would be 6. These would cancel, leaving us with our y squared. Different ways to manipulate the variables to simplify radicals in a way that will work for us. And again, different ways we can do this. One way. Power of a quotient. I can pull a power away from both terms. So the numerator has 4, the root is 4, because if I can get both of these to the fourth power, that fourth root and fourth power would cause them to cancel. And a power of a quotient says if we have a division to a power, we can apply that power to both terms. Or I can pull it away from it if they both have a power, in this case of 4. And since the numerator is x to the fourth, I can take it away, divide it by 4, I just get x. The denominator is 8. 8 divided by 4 is 2, so we have x over y squared. If I applied it to both, we'd have x to the fourth and y to the 2 times 4, which would be 8. And the reason we do this is because now I have the fourth root, and what's inside is to the fourth power. So they would simplify out, leaving us with x over y squared. However, since I applied an even root of an even power, we would technically need to have the absolute values applied to this here. Because we took an even root of an even power, we have to put the absolute values. However, realistically, I don't need it around the whole thing. It just needs to go around the numerator. And not because the y squared's on bottom. It's because it's y squared. Even if y was a negative, if I plug a negative into y squared, it's still going to come out positive. The issue isn't so much in the fact that we're taking an even root of an even power. It's because if that even root of that even power simplifies to an odd power, or simplifies to 1, which is odd, that negative issue is going to come into play. Y squared, I'm not going to have a negative error. It's still going to be positive. So we realistically only need the absolute values around the x. Some would say we need it around both, but absolute values of y squared would still be y squared. Questions on this here? And if you did forget to put the absolute values around it, that is perfectly fine. Now, I did say that there was more than one method. And really the other method, or other methods, is we split this apart. 4th root of x to the 4th over 4th root of y to the 8th. 4th root of x to the 4th is x. How many groups of 4 can we take out of 8? 8 divided by 4 is 2. It's just how we want to go about manipulating these radicals and exponents. Cubed root of 27, d to the 12th. Again, many different ways we can do it. One is separating it. Cubed root is 27 times the cubed root of d to the 12th. Cubed root of 27 is 3. And as we've seen on the last two, rewriting it as a fractional exponent, really what we're doing is dividing that exponent by 3. And 12 divided by 3 is 4. Even powers, odd root, we're good. Or, if I wanted to, I could rewrite it as d 3 to the 3rd times d to the 12th, which would be the cubed root of 3d to the 4th cubed, which is 3d to the 4th. Same thing, but if you're starting to notice, there's a lot of ways we can manipulate the exponents to get into a form that is going to help us, is going to make things nicer. Which one's correct, which one's wrong? No. Whichever one you see first is the way I would do it. Because this here, we could put it as the 4th root of x over y to the 4th. But as we've been saying, as I've been saying here, really fractional exponents with these variables, we divide the exponent by the root. So if I divide this 4th power by 4, we get 1. On bottom, if we divide this 16 by this 4th power, we get 4. And because the exponent on top, the x, went from having an even power to an odd power after we applied an even root to it, we have to put those absolute values. Because the 4th root of x to the 4th has to be a positive number. We already saw that in the example that they gave in our theorem for this year. So the denominator has an even power, so even if y was, say, to be negative, it's still going to come out to be positive. Questions on this here? Write each expression in simplest form, assume all variables are positive. Now, the nice thing about assuming all variables are positive, it means we do not have to put absolute values, because we don't have to worry about the negative case or having issues with negative coming out, so on and so forth. And what we want to do is see if we can take the 5th root of each one of these here. Now what I'm going to do, and just because again, there's many different ways to do this, I want to split it up into each of its terms. So we have the fifth root of 4, the fifth root of a to the 8th, the fifth root of b to the 14th, and the fifth root of c to the 5th. Now out of all these terms, c is going to be the nicest one of the group. Now the fifth root of 4, for us to be able to do this, we need 5 factors of a term. Well, 4, we know is 2 squared, yes? And we saw in previous lessons we can multiply the top and bottom by a radical to get it to simplify to go away. Here, I don't have a variable, I don't have a denominator. No reason to do that. Because our simplifying steps, 2 and 3 specifically, 2 says we cannot have a fraction inside of a radical. We don't have one, so we're good there. 3, a radical cannot show up in the bottom of a fraction. Still, don't have a fraction, so that's not an issue. And 1, the only other simplifying said that we cannot have perfect nth roots left over. Here, there are no perfect nth roots. So the fifth root of 4 is fine in simplified form, so no reason to do this. We're just going to leave it as the fifth root of 4 because it cannot simplify, it cannot reduce. Does that make sense? We can only put it in that powered form to see, can it reduce? If it can, we need to. Since this can't, we're not. Fifth root of a to the 8th. Well, we need to see how many groups of 5a's we have, yes? Well, for 8, if we multiply like bases, we have the exponent. So if I break it apart into groups of 8, I would have one group of, or not groups of 8, groups of 5. I would have one group of 5a's and then one group of 3, which tells me that this a to the 5th would come outside the radical. But it also means that 3 groups of a to the 3rd would have to stay inside, because every group of 5a's, every time that exponent is divisible by 5, we can pull one group out. So if it had been a to the 10th, we could have pulled 10 out. A to the 14th, we could still pull out 2, but we would have 4 left over. So a has come out. A to the 3rd has to stay inside for that part. Fifth root of b to the 14th. Well, I definitely would have one group of 5b's. Actually, I would have 2, and that leaves me with 4 left over. So really all I'm doing here is just grouping groups of 5's. I have 5, I have 10, 4 more gives me my 14, which actually tells me that I have 2 that are going to come out of this fifth root. However, 4 are going to be left inside. And lastly, c, the fifth root of c to the 5th is c. Questions on how we've gotten this so far? Now we just need to multiply this back together. Now our number, nothing simplified out. So that 4 is going to be left inside that radical. Any other numbers that we have in any of the other expressions would have to multiply together with that 4. However, it's just 4. If we look at the a's, what's inside? We still have a to the 3rd left inside the radical. However, 1a did move outside. So we have 1a outside, we have 3 left inside. So that takes care of the a's, yes? B's. Well, we had 2 that came out of the radical, but we still had 4 left inside. And lastly, c. The only c we had came out, telling me that my final answer is ab squared c times the fifth root of 4a cubed b to the 4th. So we simplify out what can come out, we leave what's inside. Questions on this here? We're ready for the next one. let's skip to this one here. I really meant to rearrange these notes so that they were next to each other. We do two examples of this instead of jumping between them. Cubed root of 2, a to the 13b cubed c to the 8th. So again, I think the nicest thing to do for this here, or may not be the nicest, but one way to look at it is to break it up into the different parts. Two is prime, which means the cube root of 2 is as simplified as it gets. It's not going to change. So if I wanted to, I can kind of scoot down the page, kind of start putting my answer together. I know I'm going to have the cubed root of 2. It's part of our answer. Cubed root of a to the 13th. We need to see how many groups of 3a will come out. How many times will 3 divide into 13 evenly? 4. Because if we looked at this, well, I could have a to the 3rd times a to the 3rd, because that's 6, 9, 12, and I would have 1 left over. So what that's telling me is I have 4 groups of a. There's 4 times I can simplify that a out of the cubed root. However, I'm left with 1 left inside. So we would have a to the 3rd outside, or not a to the 3rd, a to the 4th, because we can simplify that cubed root of a to the 13 4 times. We're left with 1 over. Cubed root of b to the 3rd. Those would simplify out nicely. It's just b. We have one group of 3 b's that we could take out. C to the 8th. Again, how many group of 3 c's can we take out? How many times can we divide by 8 by 3 evenly? Because there's 3, there's 6. However, I need 2 more to make 8. Which tells me C comes out how many times? 2. And I'm left with how many inside? 2. So our final answer is a to the 4th bc squared times the cubed root of 2ac squared. Questions on this here? All right, let's look at the other type. X cubed root of y to the 8th. Now, we've done one like this before. And the issue with this here is that we have a radical at the bottom of a fraction. Now, this one here, for us to be able to reduce it, we need that exponent and that cubed root to simplify, yes? So normally we just see how many added up to be 3, and then we went from there. However, 8 is already bigger than 3. So that's not going to work. So we can't go down, we only can go up. What is the next number after 8 that is divisible by 3? 9. How many more do I need to get to 9? 1. So what I need to do is multiply it by the cubed root of y. And what we multiply it by on top and bottom, that exponent inside the radical should not be bigger than the index. We should not multiply by a y bigger than a power of 3. Because anytime we do that, anytime we multiply by a variable that has an exponent bigger than the index, the root that we're taking, we're adding extra factors. So if we do this on bottom, the cubed root of y to the 8th times the cubed root of y, 8 plus 1 is 9. So the cubed root of y to the 8th times the cubed root of y will give us the cubed root of y to the 9th. And as we mentioned already, here, when we simplify these radicals, really what we're doing is we're taking the power and dividing it by that index, that root. And 9 divided by 3 is 3. On top, we're going to have to multiply x in the cubed root of y, which just gives us x times the cubed root of y. Questions on this here? However, we're done. We actually don't have anything else to do because there's nothing that simplifies on top and bottom. As much as we would want to simplify that y inside the radical and the y on bottom, the y in the radical is to the 1/3 power. They are not like bases. At that point, we're converting to rational exponents, which is not making things nicer. It's just x cubed roots of y all over 3. Questions on this here? As much as I want to do this one here, let's look at the other one of this type, x squared over the cubed root of y to the 13th. Just like before, we are going to multiply top and bottom by the cubed root of y, because we want to get that radical on bottom to simplify. We want it to reduce out, and to do that, we need to have y to a power that is divisible by 3. The last one, we just multiplied it by y. However, let's just make sure. So 13 is our index. We need that power, or not index, that 13 is our exponent, our power. We need it divisible by 3. What is the next number after 13 that divides by 3? 15, because we can go 14. It does not. 15 does, so that tells us we need how many more y's? 2. And realistically, this is the most we could actually multiply this by. Because if I multiplied it by another y, I will write it in here. Because if we multiplied this by the cubed root of y to the 3rd, that cubed root in y would simplify out, telling us we're not actually multiplying it by a cubed root, we're just multiplying it by y, because those would reduce out. Now if we multiply top and bottom by the cubed root of y squared, the denominator, we have 13 of them, and we multiply it by 2 more. 13 plus 2 is 15. Now the numerator x squared times the cubed root of y, no like terms. It's just going to be x squared times cubed root of y squared. The only reason we would multiply those together is if that numerator also had a cubed root. Then we could actually multiply them together. The denominator, index and power, index and exponents divide. 15 divided by 3 is 5. Telling us x squared times the cubed root of y squared all over 5 is our final answer. Questions on this here? Last one we have, simplifying. Rational exponents are nice because we're not turning them back to radicals. We're going to leave them as is. We just need to see if we have stuff in common on top and bottom, simplifying powers. First thing I notice, I have 14 divided by 2, which is 7. Yep, and it would be on top. It'd be in the numerator if there's a denominator left over. Next thing I have is x over x to the 3/4. When we divide like bases, we subtract the exponents. I'll go on and write it here, so we'd have x to the 1 minus 3/4. Our next variable is y. We have y to the 1/3 on top. We do not have a y value on bottom, so we can leave it as y to the 1/3 on top. That is all the terms on top of the fraction. However, the denominator has z to the -6th. We can't leave that exponent negative, so to make it positive, we move it from the bottom of the fraction to the top. And at this point here, I notice I do not have a denominator anymore. which is fine. So the only thing I have left to do is actually subtract 1 minus 3/4, which is 1/4. Telling me I have 7 x to the 1/4 y to the 1/3 z to the 6th. Done. We've done this before, it's just simplifying. Last one of this type. 16xy to the 1/3 over 8x to the 2/3 z to the -4. Let's work it out piece by piece. 16 divided by 8 is 2. X, really on top, we have x to the 1st over x to the 2/3. Which exponent's bigger, top or bottom? The top, yeah, so that means it's going to stay on top. So we have really 1 minus 2/3, which is 1/3. So we can write it out like we did the last one, x to the 1 minus 2/3, but we know that will be 1/3. Y to the 1/3 on top. Incidentally, no y values on bottom, so that's just going to be y to the 1/3. And no, it doesn't specifically have to pertain to y. It could be x, it could be z, it could be any of them. If we don't have something in top and bottom, we leave it. If the exponent's negative, like z is, we have to make it positive by moving it from the top of the fraction to the bottom or bottom to the top. So if that z to the -4 had been on top, we'd have moved it to the denominator and left it there. But this is it. Questions on this here? Now we're going to perform each indicated operation, assume all variables are positive. 5 square roots of y plus 6 square roots of y. The square roots of y are the same. So 5 plus 6 is 11 square roots of y. We're good there. That's just like we started the lesson with, yes? B, 12 cubed roots of 2z to the 5th minus z cubed roots of 54z squared. We cannot subtract because these are not like terms. And one of the interesting things with this here is the radicals themselves will tell us and give us hints at what we need. Because if I look at these two here, I look at the first one, cubed root of 2z to the 5th. Can I take the cubed root of 2? No. So that means whatever's in this radical is also going to have a 2, yes? Which means there's a good chance I can rewrite 54 so that a cubic, perfect cube, is going to come out, and I'm going to be left with a 2, yes? Can I take the cubed root of z squared? Well, no, so that means that the z squared is going to have to stay in here. Which also means I should be able to rewrite z to the 5th so that I have z squared left inside and something's going to come out. How many groups of 3 z's, or how many times can I take 3 out of 5? Once. Okay, well that's kind of lined up. We do have the z outside, we have the z outside. So our common part, or of this here, is z cubed roots of 2z squared. So now I just need to see how to simplify the cubed root of 54. Well, we already said 2, the factor of 2 is not going to come out. So what should have a cubed root is we can use the radicals that we have and the parts that don't simplify to see what does. So really it's telling me I have 12z cubed roots of 2z squared minus 3z cubed roots of 2z squared. Because the z cubed roots of 2z squared are the same, we're just subtracting 12 and 3. 12 minus 3 is 9. Z cubed roots of 2z squared. Questions on this here? So really, if you noticed, I didn't really tackle each one and see what simplified, break it down. I'm like, what does each one have that needs it to be the same? Because once I see that, we're good. This one's nice. 6 cubed roots of z, or 6 cubed roots of x plus 2 cubed roots of x is 8 cubed roots of x. All right, let's move on. There's not a whole lot of more explanation we need in that one. 16, 4th root of 3p to the 6 minus p 4th roots of 48p squared. Okay. 16 is not going anywhere. Can I take the 4th root of 3? Nope, 3 is prime, so 3 has got to be there. 4th root of p to the 6. If a variable has an exponent bigger than the index, it's going to have to reduce. Minus. P's already outside, it ain't going nowhere. 4th root. 4th root of 48. Probably a good chance it will reduce. But p squared won't. This is going to have to become 3. This is going to have to become p squared, and we would need a p outside. 48 divided by 3 is 16. 4th root of 16 is 2. Telling us that we have 14p, 4th root of 3p squared. That's it. I do have this posted online already. If you need it tomorrow, let me know. And we are